My name is Junyan Cao. I'm a graduate student at Shanghai Jiangtong University. The paper I will be presenting today is titled Deep Image Harmonization by Bridging the Reality Gap. Firstly, I introduce the background of image harmonization. Image composition refers to pasting the foreground of an image onto another background image to obtain a composite image. However, due to the appearance discrepancy caused by different capture conditions of foreground and background, the quality of composite image might be greatly degraded. Image harmonization aims to diminish the discrepancy by adjusting the appearance of the composite foreground according to the background. Recently, many deep learning-based harmonization methods have achieved promising results. However, there are still some issues for existing work. Deep learning-based methods require a large-scale training set that contains pairs of composite images and corresponding harmonized results. However, it is non-trivial and infeasible to collect abundant training pairs by manually harmonizing composite images. So, recent work generates pairs of data inversely, but it still requires manual labor for foreground segmentation and unqualified composite image filtering. This hinders the extendability of harmonization datasets. For example, the foreground category of test composite images may be out of the scope of training set. And in the experiments, we observed that cross-category harmonization suffers from a performance drop. However, extending the dataset to include novel foreground categories requires heavy human efforts. In this work, we propose to construct image harmonization dataset using 3D rendering techniques. This can escape from heavy manual efforts and supplement existing real-world harmonization dataset. However, due to the large domain gap, models trained on rendered image domain would suffer from a performance drop when applied to real image domain. So, we propose a novel cross-domain harmonization network named CharmNet. Our method can align two domains when training with a combination of real images and rendered images. Next, I introduce the dataset construction of our RDHarmony. We use 3D rendering software to generate 2D rendered images and use the weather system plugin to control the capture conditions. Moreover, we combine different weathers and time of the day of rendered images, then define 10 representative styles. Then, we exchange the foregrounds of ground truth rendered images in the same 2D sense with each other, producing rendered training triplets. In general, our RDHarmony contains rendered training pairs from 11 novel categories. As we focus on human category harmonization, we generate 15,000 ground truths for human and 1,000 for each other. This can produce maximally 225,000 training pairs. We define 10 styles and produce style labels to facilitate image harmonization. Then, I introduce the framework of our CharmNet. Our CharmNet contains 3 stages. The first stage is domain-specific encoding stage. The second stage is domain invariant encoding-decoding stage, and the third stage is domain-specific decoding stage. The domain-specific encoding stage projects data from both domains to the same shared domain, and the projected features of two domains are further aligned with an adversarial loss. Then, the domain invariant encoding-decoding stage encourages information sharing between real and rendered images. Finally, the domain-specific decoding stage projects the domain invariant features back to different domains by enforcing the features to reconstruct the ground truth images in each domain. By naming different capture conditions as different styles, we can exploit the style information to facilitate cross-domain knowledge transfer. We assume that the input features before the second stage are inharmonious, and the output features after the second stage are harmonious, so that the harmonization process is shared across two domains, and more useful information can be transferred from rendered image domain to real image domain. So, we propose a novel style aggregation loss to enforce the style distribution to be more concentrated after harmonization. Finally, we provide extensive experimental results to support the effectiveness of our rendered dataset and proposed method. We take human as an example novel category. Represent the performance of cross-category harmonization and cross-domain harmonization. It can be seen that without real training images from real novel category, solely using real-based categories or using rendered novel category will both lead to suboptimal performance. This motivates us to train with a combination of real-based categories and rendered novel category. We present the MSE, FMSE, and PSNR of our CharmNet and baselines trained on various training data. The results show that our CharmNet outperforms all the baselines by a large margin. Apart from novel category, our method also significantly enhances the performance on base categories. This indicates that cross-domain, cross-category knowledge transfer is also very useful. Besides, despite the performance gap between our method and the upper bound, our method has shown great potential to bridge the gap between real images and rendered images. We visualize the test results from the novel category. Compared with other baselines, our CharmNet could generate more favorable results with consistent foreground and background. Besides, CharmNet concentrates more on adjusting the foreground style to the background style without corrupting the appearance of human foreground. We also visualize the test results from base categories. It can be seen that the harmonization results of our CharmNet are more plausible and closer to the ground truth real images. That's all. Thanks.